This short video is about how to know when to use cosine, sine, or tangent, and not necessarily an exercise in how to use them, but knowing when to use which one. If you are having some trouble with such and you want some practice problems dealing with sine, cosine, and tangent, I've pasted a couple of links for you here on YouTube, so you can go to those and see how that works for you. A super neat thing about right triangles is that if you know two things about a right triangle, then you can calculate all the others. If you know the length of two of the sides, called legs or a hypotenuse, if you know the length of any two, you can calculate angles, you can calculate area of the perimeter, the length of the other side. So it just takes two, and that's what the trigonometric functions are about. So one of the things that's kind of important here is that a right triangle has this little denotation that's right through here that signifies this is a right angle. This is 90 degrees. This is 1/4 of a circle, 90 degrees. And if you see this little guy over here, this simply means that you're dealing with an unknown angle, or we're talking about this angle right here. And we use this symbol right here, theta, to denote an unknown angle. So if we don't know what angle we're talking about and we don't know how much it is, we'll just call it theta. And theta can be the other acute angle. See, all right triangles have 90 degrees and two acute angles. And these two acute angles always measure 90 degrees. So this plus this is always 90 degrees, and this is 90 degrees. And all triangles in the known universe have 180 degrees inside them. So if you add the interior angles of these, you'll come up with 180 degrees. It's the same way with a right triangle. There are certain names and words that are used for right triangles, and that is if we're talking about this angle right here, this angle theta right here, this is the hypotenuse. The hypotenuse is always the longest line in a right triangle, and this is the opposite side from the angle theta. And so if we're talking about this angle, this is the opposite side. This is the adjacent side. Adjacent means next to, and of course, opposite means opposite. And so if we are talking about the different angles that we have here, it doesn't matter if you rotate it around, the hypotenuse stays the same. The hypotenuse is always on the opposite side from the right angle. So here we have the right angle, and the hypotenuse, the longest line in any right triangle, is opposite from there. Doesn't matter how we rotate it, it still stays the right angle, and it still stays the hypotenuse on the opposite side. If theta is on the other end of the triangle, in other words, we were looking at theta here a while ago, but now we have the line over here, so that means that we're talking about this theta. Then this becomes the opposite side, just because it's the opposite part from theta. This becomes the side or the leg of the hypotenuse that is adjacent to theta, and the hypotenuse remains the hypotenuse. The hypotenuse never becomes, it never switches. So the hypotenuse is always the hypotenuse, and again, it's always opposite the right angle. So, okay, so there are a bunch of funny names to learn, but you can do it. The name theta is just a Greek letter that is used to denote an unknown angle. It looks like this. The word hypotenuse is just the name of the longest line in a right triangle. The words opposite and adjacent aren't too weird, and the edges of a right triangle that are not the hypotenuse are called legs. When the legs are different lengths, they are called the long leg and the short leg. I'll leave it to you to figure out which one is the long leg. Okay, we're going to take a look here at a standard 30, 60, 90 triangle, and I'll use it to illustrate a couple of things for you. So if we're looking at a standard 30, 60, 90 triangle, and we know that this angle right here is 30 degrees, this is the opposite side, and this is the hypotenuse. The ratio of 1 unit here and 2 units here stays the same for all 30 degrees. So if this is 30 degrees, this length right here is exactly half of the length of the hypotenuse. So if this is 5 units long, then the hypotenuse would be 10 units long. The sine of 30 degrees is a pure number. The sine of 30 degrees, it's a fraction. The sine of 30 degrees, again, it's just a pure number. the sine of 30 degrees is some length divided by some length. The units cancel. If you have 1 foot divided by 2 feet, the feet are in the numerator and the feet are in the denominator, and they cancel, so it just becomes a pure number. For example, sine of 30 is equal to the length of the opposite side divided by the length of the hypotenuse. Sine of 30 is equal to 1 unit divided by 2 units is 1/2. It is that way for every 30, 60, 90 triangle in the known universe. So here we have the 30, 60, 90. If the length of the opposite side from the 30 degrees is 0.7 units long, they can be feet, they can be miles, they can be inches, they can be yards, they can be millimeters, doesn't matter. Whatever this unit is, and this is the same unit over here, it will always be twice if we're talking about a 30-degree angle. So if I chop this off a little bit, this angle right here remains to be 30 degrees. But what happens is the relationship, the ratio of the length of this side to the length of the hypotenuse, the new hypotenuse, is 2 to 1. So whatever the hypotenuse is, it's twice the length of this over here. Let's chop it off a little bit more. So if I went to 50 units over here, the length of our hypotenuse would be 100 units for all 30-degree triangles, 30-degree right triangles. I chop it off a little bit more, and I wind up with, this is still 30 degrees here in my sketch. It's not a perfect 30 degrees. I just sort of sketched it out there. And so we have 5 units, and then the hypotenuse would be 10 units. But what happens if you don't know the angle, but you know the length of the two sides? Any two sides. Let's take a look. So here we don't know the theta, but we do know the length of the opposite side, and we do know the length of the hypotenuse. That would be the sine of theta. The sine of theta is the opposite divided by the hypotenuse. So this is just some length divided by some length, which becomes a pure number because the units cancel out. So the sine of theta is the opposite divided by the hypotenuse. Here we have the same theta. We have the same hypotenuse, but we want to know what's the length of the adjacent side. Well, the length of the adjacent side is the cosine of theta, which is just some pure number. Let's talk about this for just a second right here. So I have the cosine of theta, which is just some number. It's cleverly stored in your calculator or in charts. We'll get to that in a few moments. And it's just some number. This sign right here, most people look at this sign right here and they say, oh, that means find the answer. No, it doesn't mean find the answer. It means the amount of stuff on this side is exactly equal to the amount of stuff on that side. So this cosine of theta is just a pure number. And this right here, the length of the adjacent side divided by the length of the hypotenuse, is just a pure number. Because if it's 5 feet over 4 feet, the feet are both in the numerator and the denominator, and they cancel. So a pure number and a pure number. So let's take a look at what happens if you know the angle theta, or you don't know the angle theta, and you know the length of the opposite side, and you know the length of the adjacent side. That would be what we call a tangent function. The tangent of theta is just a pure number. And if we know the length of the opposite side, and we know the length of the adjacent side, they're just pure. That's just a pure number, because this would be like 4 feet divided by 5 feet. And the feet are in the numerator, and they cancel. So let's take a look at the next slide that I have here for us. So, all right, what happens if theta changes? Well, if theta jumps to the other side, the other acute angle, because there are only 2 acute angles in a right triangle, if it jumps to the other side, then the opposite side now becomes what had been the adjacent side. And that's because this is opposite the angle. The hypotenuse, it never changes. And so the sine, the pure number of sine, is equal to the pure number of the opposite divided by the hypotenuse. So now what happens if we've moved the theta, so now we have the adjacent side here. It's the side that's next to theta. It's the side that's next to the angle, and the hypotenuse. So the cosine of theta, again, a pure number, is just the adjacent side divided by the hypotenuse. Again, a pure number. And it's the same way with the tangent. So if I take the tangent function here, and I'm looking at this, the tangent function is just the opposite divided by the adjacent. So this is my opposite side from my theta, and this is my adjacent side. So this is just some pure number, cleverly hidden in your calculator or on some chart. It's just a pure number, like 1 or 2 or 0.7. And if we take the length of the opposite side and the length of the adjacent side, and we divide those out, because this slash right here, that vinculum right here, that just means division. So this is the numerator, that's the denominator, this is just a fraction, and it's just a pure number. So let's take a look at the chart here. So, all right, we took a look a while ago at the 30 degrees. And so here's our chart. I've kind of truncated it a little bit here. But so if we're talking about degrees, it's the first column here. And this is the first column. And if we're looking for the sine of 30 degrees, well, the sine of 30 degrees is exactly 0.5000. Correct a couple of decimal places there. Its cosine happens to be this, and its tangent happens to be that. These are just pure numbers. So if we were looking at the sine of 10 degrees, here's the 10 degree mark, and so this chart tells us that the sine of 10 degrees is 0.1736. That's just a pure number. So if we divided the opposite side by the hypotenuse, then we would come up with a sine number of this, and we could look at the chart backwards and tell us that, oh, that's 10 degrees. And we'll get into that a little later. Okay, so what happens if you know the angle and the length of one side? Well, here we know the angle. This is 50 degrees, and we know that the length of the other side is 1 unit. But we don't know what the hypotenuse is, and we want to know what the hypotenuse is. So, which function would this be? It would be the sine. The sine of 50 degrees is equal to the opposite divided by the hypotenuse. In this case, 1 divided by the question mark. We don't know what it is. Now, this just becomes simple algebra. And so we do the algebra on that, and we say, okay, so we looked up on the chart the sine of 50 degrees. Let's go back to this, see if we can find that. No, again. So, all right, so the sine of 50 degrees, I have it later. The sine of 50 degrees is the length, 1 unit, divided by some other length, and we don't know what that is, so we do a little crunching on that. I looked on the chart, and I have the sine of 50 degrees happens to be 0.7660, correct to 4 decimal places. We could go further in the decimal places. Usually, the sine, cosine, and tangent functions aren't pure numbers, aren't even whole numbers or something like that. They usually are decimals that go on forever and ever. So, correct to 4 decimal places, we're looking here that we see that 0.7660 equals 1, the length of the opposite side divided by the hypotenuse. Now, we simply then just come in over here, and we wind up doing some algebra, and we come up with that 0.7660 is exactly equal to, correct to 4 decimal places, 1 divided 1.3054. So, that tells us that the length of the hypotenuse, correct to 4 decimal places, is 1.3054. So we have to ask ourselves, does that make sense? That's a habit you should get into with all math problems. Does my answer make any sense? Well, we know that the hypotenuse is the longest line in any right triangle. And so if this leg over here happens to be 1 unit long, and we calculate that the hypotenuse is going to be 1.3, well, that kind of makes some sense that it's longer. If we'd gotten a shorter answer over here, we might need to go back and check our math. One little mistake in a whole series of things can mean that your answer gets way off. So always kind of go back and check, does my answer make any sense? Let's take a look at another one. So what happens if you know the angle and the length of one side? Well, here we have, we're dealing with the 50 degrees, We're dealing with 50 degrees here. We know the length of the other side, but we don't know the length of this side right here. Well, it happens to be the tangent function. And we'll get into a little bit later how it is that that's the tangent function and how you know that that's the tangent function. But the tangent function is the opposite divided by the adjacent side. And so if we were to crunch on that a little bit, we'd say the tangent is the opposite divided by the unknown. And so that the tangent of 50 degrees happens to be 1.1918, correct to 4 decimal places. We know the length of the opposite side, but we don't know the length of the adjacent side. So we crunch the numbers on that, and we come up with the tangent of 50 degrees happens to be 1.1918. We know the length of the other side, and then we take a look at this and we say, okay, does my answer make any sense? Well, yes, it does, except for the drawing seems to be a little off. This is a sketch. Don't ever trust the sketch. This is just a quick sketch that I made, and this isn't exactly 50 degrees here. So if this is 1 unit long, this length right here should be shorter in my drawing, but it's not. I intentionally made it a little bit longer so that we could call attention to the fact that sometimes you're dealing with the sketch, and you need to trust the numbers, not the sketch. All right, so how did I get the tangent of 50 degrees? I looked on the chart. And so here's the degree mark right here, and the tangent, correct to 4 decimal places, is 1.1918. That's how I came up with that. It's also cleverly stored in your calculator. Calculators are different, so you're going to have to, if you're using your calculator for this, you have to use your calculator and play with it a little bit to see how that works. So, how do I remember the trig functions? So I came up with my own little memory device to help me remember the 3 most common trig functions. That is, the sine of theta is the opposite divided by the hypotenuse, and the cosine is the adjacent divided by the hypotenuse, and the tangent is the opposite divided by the adjacent. That's a whole lot of stuff to try to remember, and so I thought, all right, well, let's take a look at the first letters of this, S-O-H and C-A-H and T-O-A. And I asked myself, do I know any words that start with S-O-H and C-A-H and T-O-A? And I came up with this. Soho, it's a word that I already knew. It's a place in London and a place in New York City, and it's just a place, Soho. And then I already knew the word cahoots, C-A-H, so cahoots. So if I remembered the word cahoots, that would help me remember cosine is the adjacent divided by the hypotenuse. And what word did I know that started with a T-O-A? Well, that would be toad, T-O-A-D. And so I just thought, what do I know about Soho, cahoots, and toads? And when you're trying to remember something, if you'll just think of something that's really stupid, it'll help you remember that, because it's easy to remember stupid stuff. So I thought of toads who were in Soho, who were in cahoots. You see, cahoots means to cheat people. And so these 2 toads right here are working together to cheat this toad right here. And so here we have, I imagine that we had some toads sitting in Soho, these 2 in cahoots, cheating the other one. So that's the way that I remember it. I just think of this piece of artwork right here, of Sohoian toads in cahoots to cheat each other. But there are other ways of thinking about it, and probably the most traditional way is the nonsense word that was made up, SOHCAHTOA. Sine is the opposite divided by the hypotenuse, cosine is the adjacent divided by the hypotenuse, and a tangent is the opposite divided by the adjacent. All right, well, by now you should have a good grasp on the basics of when to use sine, cosine, or tangent to solve missing lengths or angles or right angles, so we'll rip through a few examples. I'll show a problem, and you have to think to yourself, which one do I use? If you need more time, click anywhere on the screen to pause the video. Then click anywhere on the screen to start the video. Okay, what function would you use? I put a little hint for you right here. My words, Soho, cahoots, and toad. So if you wanted to find the missing length right here and you knew this degree measure, what function would you use? Well, turns out you would use the tangent function. You know the degree, and the opposite you don't know, and the adjacent you do know. That's the tangent is the opposite divided by the adjacent, toad. What function would you use? You would use the cosine function. The cosine, or cahoots as I have written over here, cosine is the adjacent divided by the hypotenuse, and we don't know the hypotenuse. What function would you use? You would use the sine function here. You know the length of the opposite side, but you don't know the hypotenuse, and you'll want to know the hypotenuse. What function? You would use the sine function. You would use the tangent function. You would use the cosine function. You would use the tangent function. What function would you use? You would use the tangent function. What function? You would use the cosine function. What happens if you know both lengths but not the angle? What function do you use to find the angle? You would use the tangent function. What function do you use to find the angle? You would use the cosine function. What function do you use to find the angle? You would use the sine function. Just remember that you can't trust toads from Soho. They are always in cahoots to cheat you. Or you can simply remember the made-up nonsense word SOHCAHTOA. Feel free to write to me at alanmorris@yahoo.com.